Hi, my name is Akin Hyatt.
Hi, my name is Lauren McCaffrey.
And this is our video summary for Lab 9. Last week we used a shear plate interferometer to visualize optical aberrations, but the interferograms produced were often hard to interpret intuitively. The next step, therefore, is to look for more efficient setups. But first, a quick review of interferometry from last lab. When two waves spatially overlap, the fields interfere with one another. The resulting fringe pattern is the sum of the two waves and represents the difference in phase between the two. A shear plate interferometer leverages this fact by interfering an aberrated wavefront with a shifted version of itself, producing a wavefront difference function. But since we don't know what the aberrated wavefronts look like, the patterns can be hard to interpret. One way we can overcome this is by using a Shack cube interferometer. A Shack cube interferometer consists of an aberration-free reference lens, a beam splitter, a cemented lens on the beam splitter, and a viewing screen. The object that we want to test is placed at the arm with the cemented lens. Instead of interfering an aberrated wave with itself, a Shack cube interferes aberrated waves with referenced spherical waves. The resulting fringe pattern is proportional to the difference between the aberrated wave and the reference sphere, producing more intuitive interferograms. As the difference between the two wavefronts increases, the phase change gets faster. In an interferogram, this is seen as thinner fringes oscillating faster and faster. The Shack cube setup is shown here with a microscope objective focusing the laser light through a spatial filter. We align the spatial filter by backing the objective as far away as possible from the beam splitter and aligning the X and Y translation. As the objective is slowly brought closer to the beam splitter, the translation knobs are adjusted as well, until the profile at the output is a clean Gaussian. After aligning the spatial filter, the test mirror is carefully adjusted until fringes are visible. The mirror is adjusted further until no fringes are visible, or when the interferometer is nulled. For an ideal Shack cube interferometer, we would expect defocus fringes to look like an Airy pattern. Although positive and negative defocus look similar, the intensity of their central fringes is slightly different. Since the Shack cube utilizes a completely different interference mechanism, we would expect these fringes to have noticeable difference to those of a shear plate interferometer. Moving the reference mirror through focus produced the following interferograms. As seen by the elliptical profile, the mirror has some residual astigmatism from manufacturing errors. Tilting the mirror produced straight-line fringes of equal spacing, oriented differently depending on the direction of the tilt. When combined with defocus, tilt simply shifts the Airy pattern from defocus. We repeated this same procedure for a short focal length mirror. It is clear from the interferograms that this mirror has less residual astigmatism, but more residual spherical aberration. Another observation is that the defocus and tilt interferograms exhibit the same behavior as those from the reference mirror. We're able to quantify the amount of aberration in the system by plotting the fringe number as a function of pupil coordinate for both setups. Fitting a polynomial to that curve gives the wavefront error coefficients. For a Shack cube, these coefficients are found by fitting a third-order polynomial and using the equations here. A shear plate curve is fitted with a fourth-order polynomial, and the coefficients are found using these equations.
Next, we can compare the shear plate and Shack cube interferometers in ZMAX. We made use of non-sequential mode to see how the misalignment of a relatively low-power doublet used as a collimating lens presents itself in interferograms. Starting with the wedged Y shear plate interferometer, we looked at the nominal collimation or straight horizontal fringes for the minimum spherical aberration orientation of the lens. We also looked at the impacts of defocus, tilt, which we expected to be asymmetric given the additional OPL term from the wedge, lens decenter, and combined aberrations. In general, we observed that it can be difficult to differentiate between the fringe patterns produced by tilt and decenter. This supports our previous findings that wedge shear plates are ideal for collimating coherent systems only. We also compared these conditions where the lens was in maximum spherical aberration orientation. As seen in the interferogram, spherical aberration noticeably distorts the straight line fringes that appear in non-aberrated collimated beam. Because of this, wedge shear plates can be useful in identifying when the lens is oriented such that it introduces minimum spherical aberration if it is not immediately present by the lens characteristics. Despite this, we continue to observe minimal changes between the interferograms for the same defocus, decenter, and tilt cases. Ultimately, these results match what we saw experimentally in Lab 8. Next, we analyze the same cases for a non-wedged Y shear plate. We observe the correct behavior for a collimated system with the lens oriented for minimum spherical aberration, yielding a constant phase difference between the sheared beams. In contrast to the wedge shear plate, the non-wedge shear plate shows defocus, decenter, and tilt as straight fringes, the curvature of the fringes, and the ellipticity of the fringes respectively. However, the magnitude and ratio of these aberration coefficients largely determines the prevalence of these features. When decenter and defocus were combined with these magnitudes, the interferogram pattern was dominated by defocus. For a non-wedge shear plate, the maximum spherical aberration pattern deviated from straight fringes to symmetrical lobes. Defocus changes the width of the lobes, decenter shifted the brightness or phase attributed to the center lobe, and tilt changed the curvature of the lobes. It should be noted that some aliasing is present in these figures, but the overall interferogram pattern is still clear. The simulation settings would need to be optimized should these images be used for further analysis or extracting aberration coefficient magnitudes. Finally, we investigated specific cases for a non-wedge shear plate and the lens oriented for maximum spherical aberration. Our previous analysis utilized small perturbations, but these cases clearly show how the aberrations are presented in the interferograms. We also added a cylindrical lens to see how this asymmetrically introduced more astigmatism into the system when the defocusing direction was parallel and perpendicular to the y-axis. However, we did not observe any noticeable changes in the interferograms due to this modification.
The setup for the simulated check cube is shown here. The following equations are used to calculate the radius and thickness of the cemented lens based on the geometry of the problem. Just like in the physical lab, we moved the optic through focus and produced varying area patterns. Since the difference between the radii of curvature between the reference wavefront and the testing wavefronts are equal at the focus, no fringes were produced. Similar to the physical lab, we found straight line fringes when introducing tilt into the system. Spherical aberration is introduced by changing the conic constant of the mirror, producing the following interferograms. When combined, it's clear to see how each aberration contributes to the pattern.